Alright guys, so this is going to be going over pages 43 to 45 from the Unit 2 test review, starting with the warm-up. So for the warm-up, what you want to do for all of these questions is you want to evaluate the logarithm, okay? So, for example, number 1, log base 2 of 32, that is asking 2 to what power is 32? The answer there is 5. Number 2, log base 8 of 1 over 64. That is asking 8 to what power is 1 over 64? Well, if it was just 8, base 8, and the argument was 64, the answer would be 2. Because it is a fraction, because it is 1 over 64, that means it's negative 2. For number 3, log base 3 of 81 is 3 to what power is 81? That is 4. For number 4, log base 5 of 25. 5 to what power is 25? That's 2. Log base 7 of negative 7. We cannot have an argument that is negative or 0. Since 7 is negative here, that means log base 7 of negative 7 does not exist. So because this is a negative on the inside of the logarithm in the argument, that is why this doesn't exist. Alright, so for this one, log base 4 of 1 over 64. Again, if it were just 64, the answer would be 3 because 4 to the third power is 64. Because this is a fraction, that is why it's negative 3. Alright, okay. So, but here, take a look at this one. Log base 1/2 of 1 over 16. Here, they're both fractions. This is like the same thing as saying log base 2 of 16 if both of them were flipped upside down. So this is actually positive 4 because both are fractions here. For number 8, ln of e to the negative 4th power, we can use our expanding to take this negative 4, move it to the front, and multiply it by ln of e. ln of e. ln, remember, is log base e. So this is saying e to what power is e? Anything to the first power is itself. So ln of e is 1. So this is negative 4 times 1, which is negative 4. Same exact thing here. You move the x to the front by expanding. Log base 5 of 5 is 1. X times 1 is x. Remember, for numbers 8 and 9, things that are the same base with the base of the exponential function being the same thing, you can just cancel them. So you could just cancel the ln and e because they're inverses and your answer is negative 4. Cancel the log base 5 and 5, so your answer is x. That's another way to do it. But I think it can be easier to just think about it as expanding because we're familiar with that. Okay, and then the last section here for what's on this page for me, number 10. Again, I expanded, moving the 4x to the front. Log base 29 of 29 is 1, or again, you can cancel those and get 4x, but 4x times 1 is 4x. Here, log base 6 of 1, 6, because it's a 1 over, that's why it's negative. And then 6 to the first power is 6, so this is negative 1. Now, for number 12, you cannot cancel the 3 and the 27 because they're not the same number. So you have to expand here. You have to move that 5x to the front. 5x times log base 3 of just 27, that's 3, because 3 to the third power is 27. So 5x times 3, that is 15x. Number 13, log of 10,000. Remember, if there is no base, that is our common logarithm. So this is saying 10 to what power is 10,000? That's 4. For 14, 2 to what power is 1 over 64? If it was just 64, the answer would be 6, but because it's 1 over, it's negative 6. And then log of 100, this is 10 to what power is 100? That's 2. Log base 7 of 1. This is saying 7 to what power is 1? Well, anything to the 0 power is 1, so this is 0. Look at the difference here with number 17, log base 3 of 0. This is saying 3 to what power is 0? Just like a negative, that's not possible. You can't have an argument inside the logarithm that is 0 or negative. So this one, just like number 5, does not exist. For number 18, again, you can cancel the log base pi and pi, or move this w-like thing to the front, and then recognize that log base pi of pi is 1, w times 1 is w. So that is the warm-up. Here are the solutions to the work from pages 44 to 45. If you want to pause here to check your work, feel free to do so. I am now going to go through them one at a time, okay? But feel free to pause to check your work before you move on. Alright, so number 1, what I did here, log base 3 of x squared minus 10x plus 21 minus log base 3 of x minus 7. I first factored the function here, and I got x minus 7 times x minus 3 minus log base 3 of x minus 7. Then what I chose to do here, there's actually two different ways to do this. I'll show you the other way as well. But another way to do this is to expand, because you've got multiplication here. So you can expand this into log base 3 of x minus 7 plus, because multiplication, log base 3 of x minus 3 minus log base 3 of x minus 7. Because you've got positive log base 3 of x minus 7 and negative log base 3 of x minus 7, those are the same thing. One's positive, one's negative. They can cancel, and we just get log base 3 of x minus 3. Another way to do this that you guys might be more comfortable with is to condense instead of expanding. So here we have, I factored the numerator into x minus 3 times x minus 7, but instead of expanding, I just condensed by realizing this is a minus here, so this x minus 7 can go in the denominator. And then the x minus 7s here can cancel because it's the same factor in the numerator and denominator. And so final answer here is the same thing that you got here, log base 3 of x minus 3. For number 2, this is done by condensing, so same way I did the second one there. I factored the numerator first, and then I took the x plus 4 here and moved it to the denominator, canceled, and final answer is log base 6 of x minus 1. So again, here I factored, condensed, simplified. For number 3, this is a logarithmic equation. It is log equals log. That is the type. I can tell because I have all of these logs and no constants by themselves. Constant again being a number. First thing that I want to do here is I want to condense on the left-hand side here, so I get log base 3 of x plus 5 times x plus 3. Then I realize that I have log on one side and log on the other side, both base 3, which means I can just set their arguments equal to each other. I have x plus 5 times x plus 3 equals 35. Now remember, when we see something like this, it's not x squared plus 15. You need to FOIL or double distribute. X times x is x squared, x times 3 is 3x, 5 times x is 5x, and 5 times 3 is 15. When I combine like terms with the 3x and 5x, I get x squared plus 8x plus 15 equals 35. This is quadratic, which means it needs to be factored. You can't factor unless you have everything on one side and 0 on the other, so I subtract 35 from each side, and I get x squared plus 8x minus 20 is equal to 0, which I then factored into x plus 10 and x minus 2 equals 0. Set each of those factors equal to 0 and solved for x, and I got x equals negative 10 and x equals positive 2. Then I need to check. Every time you have a logarithmic equation, you need to check to see if the solutions that you found are real or extraneous. Remember, a solution is extraneous if you substitute it into any argument of the original equation for x and you get a negative or 0. Has to be positive to be real. So first I put in negative 10 to the x plus 5. I got negative 10 plus 5, which was negative 5. Right there, it fails. Can't have a negative on the inside or the argument of a logarithm. So I went and I crossed that negative 10 out, wrote extraneous. I don't even need to check the x plus 3 because once it fails, all of it. Then I need to check the x equals 2. 2 plus 5, that's 7, that's positive, that's good. 2 plus 3 is 5, also positive, that's good, which means x equals 2 is a real solution to this logarithmic equation. All right, number 4. This time we have a log equals constant. I can tell that it is log equals constant because of this 5 here. See how it's not attached to a logarithm by multiplication, it's just by itself. Okay? So in order to have this be log equals constant, I need to actually set it up that way. So I'm going to add log base 2 of 3 to each side. Do that here, and then I get log base 2 of y plus 2 plus log base 2 of 3 is 5. Then I need to condense on the left-hand side. The 3 and the y plus 2, because we're adding here, are multiplied. Then, once we have this set up, it's log equals constant, we're good to go. Then we can exponentiate or drop a base of 2 on each side. We're choosing a base of 2 because the logarithmic equation here has a base of 2. So the 2 and the log base 2 are inverses, they cancel. So we get 3 times y plus 2 equals 2 to the 5th power. Remember, this 5 becomes an exponent, the base is now 2. So I'm going to distribute the 3 to get 3y plus 6, and then 2 to the 5th is 32. Then I need to solve for y, so I'm going to subtract 6 from each side. I get 3y equals 26, and I will just divide each side by 3. That cannot be simplified, so we leave it like that. But I do need to check, okay, because this is a logarithmic equation, I need to check to see if this is going to make any of the arguments positive, or sorry, negative or 0. So the only one that's a possibility is the y plus 2, because 3 will never be 0 or negative. So 26 thirds plus 2, you may not even know what 26 thirds is, but clearly it's positive. You add 2, that's still positive. So we're good. 26 thirds is a solution, and it is a real solution to this logarithmic equation. Now we have number 5. Number 5 is an exponential equation. The first thing we want to do with an exponential equation is we want to get the exponential function, in this case, e to the x, by itself on one side. So to do that, I'm first going to add 1 to each side. Okay, sorry, there was a typo, so I'm going to fix that. So I add 1 to each side, I get 2 e to the x equals 6. Divide each side by 2, and I get e to the x is equal to 3. Then I'm going to take the ln of each side, because remember, ln and e are inverses of each other, which means that the ln and the e here are going to cancel each other out. And so we get x is ln of 3. And if I didn't have that as the answer, when I put up the answers, then fix that, because this is the actual answer. It should be ln of 3, not ln of whatever else I said. Okay? Should be ln of 3 for number 5. Okay. For number 6, this is another, and for number 5 and number 6, they're exponential equations, which means you do not need to check for extraneous solutions. There are no extraneous solutions to exponential equations. You can have an exponent be anything, 0, positive, negative, doesn't matter. Alright, for number 6, same idea. We need to isolate the exponential, which in this case is e to the 4x. So first thing I'm going to do is I'm going to subtract 11 from each side. So I get negative 3 e to the 4x power equals negative 9. Then to isolate e to the 4x, I'm going to divide both sides by negative 3. So I get e to the 4x is 3. ln of e to the 4x equals ln of e of 3, because ln and e are inverses, so that's why we take the ln of each side, just like we did with number 5. The ln and the e here cancel. I get 4x equals ln of 3. Need to divide both sides by 4. So final answer, x equals ln of 3 divided by 4. Okay? And again, no need to check It is not extraneous. There's no extraneous solutions with exponentials. Alright, number 7 is also exponential, another e. E to the x over 2 is our exponential that we're going to try to isolate. So we're going to start by dividing both sides by 300. So I get e to the x over 2 is equal to 30, because 9,000 divided by 300 is 30. Again, I'm going to take the ln of each side. Ln and e cancel. X over 2 is ln of 30. To get rid of this 2 in the denominator, you need to multiply both sides by 2. That's how you get rid of a 2 in the denominator, because these will then cancel. So that's how I got x equals 2 ln of 30. No need to check. Alright, number 8. This is logarithmic. It is log equals log. I can tell that it's log equals log because I have all of these logarithms and there's no constants that are by themselves. I do have two constants, 1/3 and 1/2, but they are multiplied by logarithms, which means we're actually going to condense, that we're going to get rid of them as part of our condensing, and we don't need to do log equals constant. This is log equals log. So I need to condense. So on the left-hand side, that will turn into log base 7 of 27 to the 1/3. The 1/3 becomes an exponent over y plus 5. And then on the right, the 1/2 becomes again an exponent, so log base 7 of 25 to the 1/2. Now we have log base 7 on each side. We can just set the arguments equal to each other. 27 to the 1/3 is the same thing as cube root of 27, which is 3. 25 to the 1/2 is the same thing as square root of 25, which is 5. Instead of making it 5, I made it 5 over 1 so that I can easily cross multiply. Okay, so then that's what I did. So I got 5 times y plus 5 equals 3 times 1. So 5y plus 25 equals 3. Subtract 25 from each side. Divide each side by 5. You get negative 22/5. Then we need to check to see, is that a real solution? Because this is logarithmic, we do need to check to see, is this a real solution to our exponential, or sorry, to our logarithmic equation. So I substitute in for y here, because 27 and 25 can't be 0 or negative, so we don't need to worry about those, just the y plus 5. Negative 22 over 5 plus 5, maybe we're not sure what that is. I turned it into a decimal here. You can also see that it's obviously less than 5 because 25/5 would be 5. So anyway, it's positive. So this is a real solution. It's not extraneous, even though a lot of the times when we have a negative solution, it ends up being extraneous. In this case, it's not. This is a real solution, even though it's negative, because it doesn't make the argument negative. Okay. Alright, number 9. This one is another logarithmic equation. It is log equals log. Right away, I've already got it set up in that way, that it is set up as log equals log. So we're just going to set those equal to each other. This is not quadratic, so we're going to get all the x's on one side, numbers on the other. So I subtract x from each side first. So I get x minus 3 is 2, then add 3 to each side, and x is 5. And I should check that. Okay, so x equals 5, and I want 2 times 5 plus 3, that is 13, that works. And then we've got 5 plus 2, which is 7, that also works. So this is real, it's a real solution. It is not an extraneous solution. So 5 is real here, but we do need to check because it is logarithmic. Alright, so for number 10, this is logarithmic as well. This time it's log equals constant. The 4 over here being by itself, that's the constant. The 1/2 is not, because that can be condensed to being an exponent of the logarithm, but the 4 here is by itself. So we do need to condense on the left-hand side. So since this is an addition, we're going to multiply, and then also because we have the 1/2 here, that is going to become an exponent, 9 to the 1/2. 9 to the 1/2 is 3, because 9 to the 1/2 is the same thing as the square root of 9, which is 3. So we've got log base 4 of m times 3. So what we can do is we can drop a base of 4 on each side. So log base 4 and the exponential base of 4 here are going to cancel on the left. And so that's m times 3, or 3m. And then over here, 4 to the 4th, well, 4 to the 4th is 256. So we are going to go ahead and just divide both sides by 3. 256 divided by 3, that is not an integer. We're going to leave it like that. But we do need to check if it is an extraneous solution, which is right here. The only place to plug it in is just the m here. Well, it is a positive number, which means it works, because it's just plugged in for m itself. So since 256 over 3, even if you don't know exactly what it is, you can tell that it's obviously positive. All right, number 11. This is an exponential. The exponential here is 2 to the x minus 1 power. We need to isolate the exponential. So we're going to subtract 6 from each side. We get 2 to the x minus 1 equals negative 5. Then we're going to go ahead and take the log base 2 of each side, because that log base 2 and the exponential base of 2 are inverses, they'll cancel. When we do that, we get x plus 1 equals log base 2 of negative 5. Maybe you already see the issue. Add 1 to each side, and the answer we get here is log base 2 of negative 5 plus 1. The problem is we can't have an argument that's negative, okay? We talked about this in the warm-up. So for getting the plus 1, it's irrelevant. This right here, the log base 2 of negative 5, that doesn't exist, which means the whole answer doesn't exist. So there's no solution to this problem. We don't even need to do any checking. We wouldn't have to check if it was, because it's exponential anyway, but regardless, the answer we got is not possible, which means there's no solution. The answer does not exist. All right, and last one here, number 12. What we're going to do here, first of all, this is a logarithmic equation. It is log equals log. You can see that there's no constants. They're all log base 7. So I'm just going to go ahead and condense on the left-hand side. Log base 7 of x minus 7 over 2x plus 1. And now I have log base 7 on each side. I can go ahead and set their arguments equal to each other. I'm going to turn 3 into 3 over 1. So that I can make it easier to cross multiply. So I get 3 times 2x plus 1 equals 1 times x minus 7. Okay, we're going to distribute. So we get 6x plus 3 equals x plus 7. Subtract x from each side. 5x plus 3 is negative 7. Subtract 3 from each side. 5x is negative 10. And then we're going to divide by 5 on each side and get x is negative 2. Then we need to check to see if that negative 2 is a real or extraneous solution. So I plug it in. I'm going to plug it into the x minus 7 first. Negative 2 minus 7 is negative 9. That's a negative number. It already fails. We don't even need to check this one. Because it was the only solution that we found, and it was an extraneous solution. Sorry, the US got cut off here, but this is supposed to stay extraneous. Because it's the only solution we found, and it's extraneous, that means there is no solution to this equation, okay? Unlike one of the ones we did earlier where there were 2 solutions and only one of them was extraneous, the other one is real, then that's the solution. But in this case, because there are no real solutions, that means there is no solution. So that's the end of pages 43 to 45. We'll do the rest of them, 46 to 50, in a different video. Thanks, guys.